Okay, so welcome back, and in this video we're going to be looking at more of the reactions of the halogenoalkanes. We're going to be looking at predominantly nucleophilic substitution reactions, but it will also look a little bit at elimination reactions. So you're going to need your notes, and we're on page 14. Okay, so we're going to be looking at the nucleophilic substitution reaction with ammonia. So we start off here with our halogenoalkane, and we have excess ammonia, and we're going to replace that halide ion, that halogen ion here, this X, with an NH2 group, and that turns it into what we call an amine, A-M-I-N-E. And the other product we get is we get ammonium bromide, chloride or iodide, whatever the X was. Now the mechanism is very similar to the one we've done before. You only need to know the mechanism with primaries, not with secondaries or tertiaries, so it's quite straightforward. So we'll just be going to be doing our SN2 mechanism. There is a little bit extra in it, and I'll go through that. So we start off in a very similar way to the way we started off the previous mechanism. We have our chloroethane molecule. It has a dipole in it, delta negative, delta positive. We have our ammonia molecule, our NH3, lone pair on the nitrogen. That attacks the delta positive carbon, pushing the electrons out. We can draw our little transition state. Technically, we don't really need it for this one, but it's always a good idea to draw it. So again, we've got our Cl group going out one side, and our NH3 coming in on this side. So as this group goes in, this group goes out. And we get our product. So that's our transition state there. And our first step, at the end of the first step, we get this as our product. So we've got 1, 2, 3. You've got H. You should notice that I've got a bit of a problem here. I've got too many H's here. This is now a positive because the electrons have gone totally onto that chlorine, and the nitrogen isn't actually bringing any extra electrons with it. So we get this as the end of the first stage. Well, it doesn't stay like that, especially if I've got some ammonia present, because ammonia is such a good nucleophile that it can pull off one of those hydrogens. So that lone pair is going to pull off that hydrogen. It's going to force the electrons then back onto that nitrogen. I'm just going to draw this down the page. So I then get my NH2 group here. This is my amine. This is ethane or ethane amine. So ethane, amine, eth, 2 carbons, and no carbon doubles, amine, because I've got an amine group on the end of it. And these two, all these extra bits are joined together, so I've got NH4 positive, Cl negative. I've got ammonium chloride as my secondary product. Okay, so I'm now going to do the reaction between 2-iodopropane and water. So again, I get my ROH, and I get, this time because I've lost the iodo group here, I get some H3O positive, I negative. Okay, that bit I'm going to talk about in a minute, but I get the I negative coming off, or the X coming off, I should say, because this has been replaced. So again, looking at this reaction, I've got my propane. I'm going to put the I there, CH3, just keeping these bits out of the way, CH3, and I've got this bond here, delta negative, delta positive. The OH group, the water molecule, lone pair on the oxygen, I can say that pushes in, pushes out, and I get this. Again, I've got the same problem that I had before. I've now got this, so there should be hydrogen on that. Hydrogen there. I've got this group here with this positive charge, and I've got my I negative floating around somewhere there. So what I'm actually going to get is another molecule of water which is going to grab off that hydrogen, pushing the electrons back onto that positive. Oxygen very rarely sits there along with the positive charge on it. And I get my OH. I've still got my CH3 and my CH3 and my H, and I get H3O positive, I negative, which we can usually just write as HI, hydrogen iodide. This is an acidic molecule. This is what we consider an acid, and this is a reasonably strong acid. The hydrogen and the iodide split up when they're in water to make an acid. Okay, so we're now going to be looking at page 15, and we're looking at the elimination reactions. And it's a slightly different reaction with the halogenoalkane. This time it's being heated strongly with an excess of concentrated alkali dissolved in ethanol, not in water. Okay, all of these reactions, you don't want to dissolve things in water. If we dissolve them in water, we're just going to get large amounts of the alcohol, and we don't want that in this case. So what is an elimination reaction? Well, it is the removal of one or more groups or atoms from adjacent, that's important, carbon atoms, forming an unsaturated molecule. So if we take this as an example, I'm going to remove that bromine, but I'm also going to remove a hydrogen on an adjacent carbon. Can't remove that hydrogen because it's on the same carbon, but I'm going to reduce the adjacent one. The other hydrogen I could remove is this one. Doesn't really matter because I'm going to end up with the same molecule. I'm going to end up with propene. Whether I put the double bond here or here, it's still going to be propene. Okay, and I get hydrogen bromide as my other product. In this case, the OH ions act as a base. You've seen them before acting as a nucleophile, well in this case they are acting as a base, and that's important. Okay, so would one bromopropane give the same product? Well, if the bromo was on this group and the hydrogen on here, so again you remove this one, so yes it would. Because if you think about what one bromobutane looks like, you would see, again, I've got to remove an adjacent hydrogen. So in this case, I've only really got one choice about which carbon I remove it from, and that would be this one. But it would put the double bond here. So if we draw the double bond in red, we took the double bond there, you'd end up in the same place. Okay, but when you deal with something like 2-bromobutane, again with concentrated potassium hydroxide, again in ethanol, so here again the hydroxide is acting as that base, we have a bit of an issue. So if we draw out 2-bromobutane, we've got the bromo on this second carbon. So now there are actually 3 different products that I could make out of this, because if I remove the bromine and one of the hydrogens from the first carbon, I'm going to get the first of my products, which would be but1-ene. So I'm going to get this molecule, and this is the first of my possible products. Or I could take the bromine and an adjacent hydrogen from the third carbon, so from this carbon here, and this time I would get either this version, which you should recognize, be able to work out, is Z-but2-ene, and where there's a Z, there will also be an E, so I can also get the E version of this, where there's 2 CH3 groups are on opposite sides of the molecule, and that is E-but2-ene. ene. So I can get, that's just but1-ene, which doesn't have geometric isomers, remember, or I can get Z-but2-ene, make sure it's a Z, or I can get E-but2-ene. And when I say 3 possible products, what you probably get is all 3 of them. If you did this in a mixture of ethanol and water, you would also get the alcohol coming off as well. So you get basically 4 different things. You'd get the butes, butene, you'd also get a butanol as well if you mixed it in with water as well as the ethanol. So that finishes this little video looking at some of the nucleophilic substitution mechanisms and also looking at the theory behind the elimination reactions. In the next video we're going to go on and look at the practical involving the elimination reaction, and we're going to look at the last reaction between halogenoalkanes and potassium cyanide. But till then, take care, stay safe, bye bye.